Welcome to my presentation. My name is Wens, I'm from MinDCet, and today I will present you about driving power applications to the next level with GaN. A GaN HEMT is no MOSFET. That is clear so far to everyone, I believe. Especially the pitfalls are the tighter controlled gate turn-on voltage, lower threshold voltages, and significantly faster turn-on and turn-off times, meaning high DVDT. In combination with the lower gate source to gate drain capacitance ratio, this means prone to parasitic turn-on. So how do you drive GaN correctly? Well, there are a number of things to overcome and to look at. First of all, you have the PCB level where you want to keep all parasitic inductances and loops as short as possible, both on the gate, but also on the supply. And then, of course, there is the key part in the whole system, which is the gate driver IC. The dead time control needs to be very tightly. The high side, low side delay matching also needs to be very close. The VDT immunity to the gate driver, especially the high side, is key. And the negative source voltage spikes due to the ground inductance, which is inevitable, need to be overcome, and the gate driver needs to be immune against that. And there is also gate overcharging. So a good synergy between the power stage and the gate driver is key. The MDC 901, here shown as a block diagram, has a number of unique features to address these issues and make sure that you get the maximal performance out of your GaN power stage. I will not go into detail of all of them, but a very close controlled floating regulator, both on the high side and low side, to control the gate within its specifications without gate overcharging is one of those key factors. But also the dead time control, which can be configured in many different ways, is important, and the matching between high side and low side. Another unique feature is the charge pump that can drive the high side into 100% duty cycle. We will use our MDC 901 gate driver together with both GaN systems 100-volt devices and InnoScience 150-volt devices to do a comparison of performance and parameters. These two devices, as you can see, are electrically quite close to each other, although the InnoScience is a bit smaller in physical size and has a higher operating voltage range. The other parameters like RDS-on and gate charge are similar. Both of these devices are mounted on an evaluation board, as you can see here, together with the MDC 901 gate driver. Not shown here or not visible here is the active heatsink with a cooling fan on the bottom, which is connected to the PCB by means of a thermal interface sheet for a good thermal contact. Then if you look with the thermal camera to a few use cases, we see here, for instance, 48 volt in, 12 volt out with the load current of 16 amp in a buck configuration. Then we see that on the GaN system board, we have a temperature of the low side, which is the maximal temperature in the system, of about 45 degrees C, where on the InnoScience board, the low side is 94 degrees C. Although the efficiencies are virtually equal to each other, so also the power being dissipated is very similar in both boards, you do see a much higher temperature at the InnoScience devices, which is of course related to the fact that they are around 5 times physically smaller in package size compared to the GaN system. So that also means that the power density is quite a bit higher, and of course that makes it more difficult to dissipate the heat through the thermal vias of the PCB towards the heatsink. Here's another case really suited for GaN is very small duty cycles, because the steepness of the flanks compared to a MOSFET gives a clear and significant advantage. So here we go from 48 volt in down to 3.3 volt out. So pretty big conversion ratio for a buck converter. The load current in this case is 15 amps and we are switching at 300 kilohertz. As we can see, the efficiency is again pretty similar, although the InnoScience devices have a slightly higher efficiency, which is related to their gate charge, which is slightly lower, and also their RDS(on) is slightly lower, but it is very similar. So also the dissipation will be quite similar, although slightly higher for the GaN system devices. Nevertheless, we see that the GaN system devices remain relatively cool around 45 degrees C, whereas the InnoScience devices again were a bit hotter around 83 degrees C. So despite the higher efficiency of the InnoScience devices, they also run hotter in this application. It should be mentioned that the previous slide and also this slide is performed, so the experiment is performed under room condition temperature. So yeah, of course, in an application, especially inside an enclosure, the ambient temperature might be quite warmer, and yeah, this could pose a limit for the use of the InnoScience devices rather than the GaN system devices, which run cooler. But of course, this will largely depend on your application, your setup, the thermal system, and yeah, the mission profile. Just to say that it doesn't mean that one device has a higher efficiency, that it also is per definition better or yeah, running cooler than a device with a little bit lower efficiency. You really need to look at the full thermal system. Then if you look at pure efficiency comparison in both cases, so from 48 to 12 and from 48 to 3.3 volts, we see that both the GaN systems evaluation kit and the InnoScience evaluation kit in combination with our MDC901 gate driver perform very similar. So the efficiency, yeah, is maybe a few percent higher for the InnoScience devices, but it's really similar to each other. And again, the larger physical package area or size of the GaN systems will allow to dissipate more power, or for the same dissipation as the InnoScience device, run a bit cooler, whereas the InnoScience device has a slightly higher efficiency. These two parameters, yeah, need to be traded off against each other, and it will really depend on your application to see which one is the more suited. We have tested also a third evaluation board with our MDC901 gate driver. This one uses the EPC 200 volt GaN HEMTs, and we have not taken it into account with the other two as a direct comparison because the voltage range is even more diverting. So here we really look more at higher voltage applications. Again, in the configuration of a buck converter, and the thermal system is very similar, although here the GaN system HEMTs are mounted not on the front side of the board, but on the back side of the board, allowing almost direct thermal interfacing with the heatsink, again through an electrically isolated but thermally well-conductive thermal interface material. So here we have use case of a bus voltage of 100 volts, which is converted down to 12 volts. And over different load currents here, you see that the efficiency from a certain load onwards is well above 90%. The power dissipation that we see is in the order of a few watts up to 8 watts, which is consistent or in the same order of magnitude as the previous experiment that we did with the other two evaluation boards. Here you see a zoom in of the switching nodes of this EPC board, where you see that in fact the switching node is very well controlled and very well damped. So you really get an almost ideal waveform with very high DVDT, around 30 volt per nanosecond for the rising edge and 45 volt per nanosecond for the falling edge. So these are close to ideal waveforms. So I conclude that our MDC 901 is really a versatile driver for diverse applications, and it can work together with different types, different brands, different styles of GaN power devices of different voltage levels up to 200 volts. Yeah, many applications are enabled by this combination of different power stages, limited, not limited to the ones mentioned here. So we can conclude that improper GaN gate driving can induce many problems and will potentially offset the benefit of GaN. But GaN driving can enable the true benefits of GaN, or good GaN driving, meaning transient speed, low losses for high power density, and in the end we have a true 200 volt driver. So we've presented our state-of-the-art solutions using different brands and different types and voltage ranges of GaN power HEMTs using the MDC 901 as a gate driver. And this enables a range of enhanced applications, including DC-DC converters, LiDAR drivers, Class D audio, BLDC motor drivers, and much more. Today still, but this will change in the future as we go, it's already changing. GaN HEMTs are still not the cheapest around, but you can get the best benefit out of them if you get your gate drive right. I'd like to thank you for your attention. We are MinDCet. We are located in Leuven, Belgium, close to Brussels, and you are very warmly welcome if you're in the neighborhood. Thank you.